Welcome to the most difficult talk of the day. So in the morning it's easier, you've had your coffee and everything. Lunch comes, food is transferred into calories right now, broken down and all that good stuff. Good after lunch discussion. And then here comes this talk, which is going to compete with your body's tendency to go to sleep for digestion. The title of this talk is going to become obvious towards the end. So, sheer folly. Notice that folly is in code font. So, the question I would like to discuss in this talk is why do we care about C++? With the emergence of so many other languages, why do we care about C++? And more generally, why do we care about system languages in general? Why do we still care? There's a couple of reasons, there's many reasons, but a couple I would like to talk about. Number one is something that many people tend to forget. I interviewed probably more than 100 people for Facebook, very, very many people, and very few of them understand when a high-level language gets, when the rubber hits the road, so the high-level language gets transformed into code that's ultimately executed. Very few people remember how data, literally how it sits in memory. One great thing about low-level languages such as C and C++ is that they allow you to literally tell every byte where it goes. Actually, literally, like byte-level control, every byte, every single byte this guy is gonna sit here, this guy is gonna sit there. And this offers a tremendous amount of control and advantage to certain applications. To wit, at Facebook, we defined our own string. I know it sounds very script kiddie. We defined our own string because we decided that std string does not exercise enough layout control and does not have guaranteed performance enough as much as we needed in our server-side applications. Well, the obvious question comes. This is what the Incan middle manager said, right? Let's not invent the wheel here, as the Incans didn't know about the wheel in the first place. All right, we're going to need some canned laughter here, if you can, in the audio. All right, great. So, it's the obvious question comes, why do we want to actually write a string that implements the actual std string interface as opposed to defining our own better string.h, right? There are many demotivating factors, like, there's this long-going story, like std string, using std string as a container, it has begin and end, but, that's pretty much where the support starts, so that's not really working all that well. Very few people actually manage to successfully treat std string as a container. Among other things, it's the element type of the container, which is char or wchar, is not suitably encoded, for example, in UTF-8. It's not very good as a container. Well, what do you think about std allocator? Hands up if you like it. All right, survey says. Well, who knows about char traits? Knows, not likes, knows. All right? We all know about char traits. Not all. We all who rose the hand know about char traits, the failed attempt to include encodings into the C++ standard. Nobody could use them successfully. Well, there's also algorithm integration. If you want to find something in a vector or a list or a map, you use a certain API. If you want to find something in a string, what do? Well, you're going to go to strings, little ghetto functions and algorithms, and you're going to go there in the ghetto and do stuff. It has its own little province of algorithms. So, you guessed right. How about copy and write implementation for strings? Does it work?
Not anymore.
Not anymore. Congratulations. Became fail. By the way, I know this is not grammatically correct, but right, this is the hip thing to say, is fail, this is fail, and stuff like that. Epic fail, if you wish. All right, so we have all of these demotivating factors. Of course, we have a lot of motivating factors that convince us to say, you know what, actually the std string interface is very good. Let me enumerate the long list of motivating reasons. In the immortal words of George Costanza, right? Because it's there. So everybody has heard of std string, everybody's used it in their career. It's documented thoroughly, has a very precise definition. It's, and most of all in our code at Facebook, actually we did have a lot of code that used std string. And most importantly, we did have code of which performance profile showed string creation and manipulation near the top of the costly functions. So we're motivated to say, let's build an exact replacement for std string, a drop-in, and then we're going to replace it in one shot, and the whole program is going to run faster if we align our ducks right. And actually, this is exactly what we've done. So we've implemented fbstring, which is a drop-in replacement for std string, and then essentially we built our own implementation of the GCC library, the G++, GCC C++ standard library with fbstring baked in. And then we link against it, and without absolutely any change, code that uses std string is going to be routed through our primitives. Question? More often than not, this has been a huge gain, and sometimes it's been a modest gain, and sometimes it's been immeasurable gain. Fortunately, we didn't see any case in which there was a net loss. What's the secret sauce of fbstring? So we have two. That's not the typo, actually. 1 and 1. They're equally important. All right, I took a little license there, Number one, it's data layout control, and number one is cooperation with the memory allocator. So what do I mean by data layout control? Well, fbstring has a 3-tier layout instead of most implementations that have only one approach to layout or two maximum. fbstring uses 3. Why? Because 3 is greater than 2. It's good to know math, All right, so we have 3 strategies that don't overlap. So we have in-place storage, the so-called small string optimization, or small buffer optimization, or small vector optimization. Each community has its own, its own name for it. But essentially, in the body of the string, if the string is shorter than 23 characters including, then we're going to store it right there. There's no allocation. In the body of the string, there go the characters. Second, we're going to say, well, if you enlarge the string, it's not going to fit in the, the body of the string alone. We're going to go with eagerly copied strings. So you allocate the memory, and then you copy it. Whenever you copy the string, you copy the memory with it. So we call that eagerly copied memory. And then there's some other threshold that's going to be broken at around 200 characters. Beyond 255 characters, we're going to use copy and write and reference counting. The interesting change of phase here is that beyond 200 bytes, the cost of doing increment and decrement atomically becomes smaller than the cost of copying the actual buffer. See what I'm saying? So it's, if you had like a string that has like, for example, 50 characters and you wanted to just copy, just reference counting, that's a net loss. Because reference counting at such a short string, you're better off just copying the bytes, because essentially one reference count increment is going to cost you as much as copying 200 bytes. So then let's do the eager copying for these medium-sized strings, and then when the string becomes indeed large, to justify the use of reference counting, we're going to use reference counting. So this 3-tiered strategy has essentially solved all of the relative disadvantages of each strategy in isolation. So we're good to go pretty much at any length. Now let me illustrate how the layout actually, what the layout looks like. So you see this is actually the exact same, the exact same buffer. This is the body of the string. No photos here, you know. No photos. Take his camera. Security. All right, so this is the exact same, it's the body of the string, of FB string. And it could be looked at in two different ways. Way number one, if you find here 0xff, then the whole buffer is going to be interpreted like that. So any function of FB string, first thing it's going to do is going to look at the last byte in the string, right? And if it's all ones, then the interpretation of the rest of the buffer is going to go like this. If it's anything but, everything else in the string is going to be interpreted like that, and that's how it works. All right, what with the 9 there? You know, can anyone say, like, what's the role of the 9 in there? Why did I put 9? Because I can tell you, like, the size of this guy is like 3, 6, 7, 8, 9, 10, 11, 12, 13, and then a terminating 0. So what's the thing with the 9? Yes, Ben. Huh? Unused bytes. Well, Ben is cheating because he works at Facebook already, so we might have talked about it in the cafeteria. Someone else? No, sorry. So the answer is correct, but why would I want to do that? Someone else but Ben. Yes?
Well, it means that you can, when you're manipulating a string, you can decide whether or not to spill it without actually scanning the string to find out how long it is.
So the answer was, if you keep the number of bytes unused here, you don't need to spill it.
Well, you can decide whether or not to spill it.
You can decide whether or not to spill it. Yeah, but I could decide just as well if I just kept the length in there, right? Yes?
So if 0 unused bytes, then you double use this, the last byte as the terminator of the string.
You should have, you should have sneezed right then. This is it. Yes, Alex.
So you could keep appending to it?
Huh?
So you could append to it past that point?
No, actually, he just answered. So essentially what happens here, sorry?
I don't work at Facebook.
He does, and he doesn't work for Facebook, Alex, you know? All right, so what happens is very simple. We gain 1 byte for nothing. Because if you keep the number of bytes unused, as the string grows, at some point you have a 0 here, which is the different, 0 bytes unused. And at this point, this 0 becomes red hot because it does double duty. One is a 0 terminator, which is nice to have for that sister thing, right? And second, it's also going to say there's 0 unused bytes, so it allows you to compute size in O of 1, right? I always love talking about this. You know, it's my contribution to the community, honest. I invented this. This is awesome. I know it's little, but this is all I could do, you know. I tried machine learning, all that good stuff, you know. All right. So the key here is that we have control. And let me actually detail a bit. So it's not only this little detail, but it's also like you have these small strings, and then you have medium and long strings. And for long strings, it gets interesting because the long string must have the reference count. And I'm not sure you remember, but in the long string, you had an atomic reference counter to the left of the pointer to character at negative offset. So you exploit the fact, and quite honest, you exploit the fact that there's 2 ways to go into memory, and it's O of 1 in both directions, right? So we exploit that we have a pointer there into the middle of a buffer, and we know if we go 4 bytes to the left, we stumble upon a wonderful 32-byte reference counter, which is going to be there. But if the string is not long, it's not going to be there. And if you try to, access it and it's not there, what's going to happen? A terrible error, right? So this is a disadvantage, right? So control is key here. We get to literally say, I mean, imagine this is the wet dream of any chemist. I would like to build a molecule in which I put the atoms by hand. And this is exactly what happens here. We get to take data by hand and put it wherever we want it to be, and it goes there, right? It goes exactly, the C and C++ compiler is such a dumb servant. It's sort of, it's like the sorcerer's apprentice kind of legend here. in which it does exactly what you tell it to do. If you tell them just the wrong thing by a little, it's going to be a disaster. But as long as things stay friendly, it's going to do well. So control is a keyword here in systems languages. The performance impact of this is huge because, as I mentioned, very few programmers today remember where data sits in memory. So I'm interviewing Java and Python programmers, not to say bad things about either of these languages, but come on. All right. So I interview people and I say, define for me a sparse vector. And everybody's creating like a little class and say, I have index, I have value, and then there's an array of these, and it's an array of tuples, which makes a lot of sense. It's a good representation for certain purposes. But what they forget is that an array of tuples is actually an array of references to tuples. So every tuple is going to require one memory allocation, one indirection every single access, as opposed to what you need to have, which is essentially an array that's contiguous with tuples. And each tuple should be in situ right there and then inside the array containing the index and the number. And people forget, they consider that zero cost. And when it's actually huge cost. It's a huge constant that multiplies everything. And actually, to sort of belabor the point a bit, actually, another mathematical truth is that 23 is much greater than 15. Why am I saying, so 23 is the maximum number of characters we can store in the small string. So far, so good? All right, 15 is what other implementations of string that employ this optimization offer. GNU has its own __ vstring structure, and Microsoft Visual Studio implements, actually in std string, it implements this optimization, again for strings up to 15 characters. So essentially they have like 2 pointers in the string, right? 2 pointers is like 16 bytes, right? All right, so this looks okay. I mean, 23, 15, it's not a big deal. Actually, it is. And here's the problem. Here at Facebook, it turns out we have very many protocols and file formats that actually store integers as strings. That's not bad because most integers are small. This maxim, it's a classic. I mean, everybody says most integers are small. In a program, in any given program, if you take a photo of it, right, and you count the integers, small integers, everything is going to be 0, first of all, like 90% is going to be 0, right? And then you're going to have some ones and twos and fives and tens and 100s, and very few there's going to be like, 16 million and 23 million and stuff like that, right? Most integers are small, except if they're random. Guess what's random? Your user ID. User IDs at Facebook are random. Like IDs at Facebook for everything, cities, countries, users, pages, you name it, is a randomly generated ID, 64-bit. Now, math question. How many numbers fit in 20 bytes, but not in 15? How many 64-bit numbers fit in 20 bytes, but not in 15? Because you'd think like 25%, right? How many? Like, in first approximation, all. Because you decrease, like you take 10 to the power of 20 minus 10 to the power of 15, which is 10 to the power of 20. Right? So this is it. So essentially, with this, all IDs are going to spill into allocated memory. With this, none is going to spill into allocated memory. Because like 64-bit is like maximum like 20 characters. 21 if you want to have a sign with it. You could append a plus, add a plus. Question?
I just want to make a small technical comment. It turns out that Microsoft's implementation, what you said is correct, it's 15 bytes is the storage. So it'll actually hold 15 characters, or it'll hold 7 characters, depending on whether they're long characters or they're short ones. GCC actually counts characters, not bytes.
Thank you. So the point was, which was only half mic. So the point was, in GCC, we're talking about 15 characters, which means in 16-bit representation, you have like actually 32 bytes. And in Microsoft, they only count the bytes. So it's either 15 UTF-8 characters or 7.5 UTF-16 characters. Thank you, Scott. All right. Yes?
Is it available or allowed to configure at compile time a different value for as a parameter you have a fixed usage size?
Can you configure during compilation this size? The history goes like this. Initially, like years ago, I wrote an abstraction called FlexString. I published it in an article. It's available online. And then FlexString did have the configuration. It was very nice. And then, I joined Facebook. I worked for Facebook. I figured out that we have a need for this. And I took that implementation and made it as robust and simple as I could. And in that process, I eliminated that possibility. But it would be, right now, it would be a good step to take, to take again. All right. So indeed, 23 is much greater than 15. I love math. Math is good. All right, so now there's the French Connection. Great movie, great allocator. Jason Evans, just so you know. He's not French. He's born and raised, okay? Jason Evans wrote a great allocator, which is actually I think it's on Fedora or FreeBSD. So it's essentially the allocator of FreeBSD and a very good allocator. And it's the allocator we use everywhere at Facebook because it's so damn good. Everything you throw at it, it's going to do better than everybody else. It's a great allocator. Now the question is, what do you do if you have a great allocator and a crappy interface for std string? Well, you're going to do what you can to communicate between the string and the allocator. So to clarify why we use JMalloc, it's very highly concurrent, which we care because everything is concurrent at Facebook. It's very cache friendly, so Jason has taken a lot of steps towards improving cache locality of his code, of his algorithms. And cache locality, is a good proxy for a lot of, sorry, not cache locality, data locality is a very good proxy for cache friendliness. And as I said, it's extremely fast. It just screams. So we decided, Jason and I have talked and ployed about this, scheming and all that good stuff. So we talked about this, let's make JMalloc discuss, std string, call into JMalloc, obtain additional information, all that good stuff. So FB string does two interesting things. One is it allocates memory in allocator convenience slabs. As I'm sure you know, most allocators, and JMalloc is no exception, don't allocate like if you ask for 53 bytes. They're not going to give you 53 bytes. They're going to round it up to whatever is convenient for them, probably 64, right? Similar, if you ask for 4 megabytes and 1 byte, 4 megabytes plus 1 byte, it's not going to give you exactly that number. It's going to give you round it up to probably 8 megabytes. And all of a sudden, we're looking at a significant slack. So looking at a lot of memory that the allocator allocates because it's forced to by its own granularity decisions, but you're not able to use. What's that called? People who design memory allocators? Huh? What kind of fragmentation? Internal it's either internal or external. I always forget which. Okay, Jason should know. All right, so we have this fragmentation, which is essentially memory that the allocator allocates. It gives to us, but we lose information about it. And it's all these black spots in memory. So how we solve that is FB string is going to know what's convenient for JMalloc. And it's going to say, you know what, whenever I ask for 53 bytes, I'm going to allocate capacity of 64 bytes. And then I'm going to use that going forward as the capacity. And if you continue to grow that string, it's going to continue using that memory instead of reallocating all that stuff, right? Was this clear? All right. Ben said so, so the smartest guy in the room said so, I'm going to continue. Okay, and second, gmalloc, as many other allocators, actually offer in-place realloc. So if if you allocate a lot of memory and then you want to grow it, what std allocator does is, it gives you the option, you kill whatever you have and you move it elsewhere. But with gmalloc, you can actually say, you know what, if you can, actually grow in place, right? Grow a bit more. And that's great because if you build large strings, the large string being built in a loop is going to be the dominant thing in memory at that time. So you're going to continue just growing that thing, and you're going to have algorithms that instead of being quadratic are going to become linear. And this is huge, right? And to clarify what I mean by the expanded interface, I have a very simple function here, which is actually really a collection of special cases. Good malloc size. If you ask for 0 bytes, it's going to give you 32 bytes or whatever. Yeah? If you ask for 53 bytes, it's going to give you 64. If you ask for 257 bytes, it's going to give you 512, and so on, right? So FB string, whenever you want to, it needs to grow, is going to say, give me this many bytes, but then it's going to use this result as the new capacity. Make sense? All right. So this is good. No more internal fragmentation. Awesome. All right. Second, we have a sort of an interesting tidbit here. When the memory is too small, there's never going to be growth in place because it's slabs. It's just, it's constant size slabs of memory. But when it gets to 4 kilobytes, from that point on, it has the ability by design to grow in place. So we also have that enumerated value that tells us when to actually consider growing in place. And last but not least, this is a sort of a more hairy routine, which is essentially, so Jason and I sat down and talked, and Jason had to write the routine in a way that satisfies C callers as well as C++ callers. So it's a bit more clunky than it could if it were like a C++ nice function. So we have take this pointer. You see it's past the address of the pointer because the pointer could be relocated, could change. All right, allocate this size, possibly with this extra bytes at the end. So, you prefer size plus extra, but you're okay with size. Deposit the resulting size in R size and obey some flags, among which most notably there's a flag that says don't move memory and stuff like that. With these 3 extensions, FB string can communicate with the allocator exactly how it wants memory to be handled. Yes?
Copy, does the R size tell it how many bytes to copy, or will it never copy?
If you ask for a copy...
If this function can't reallocate in place and has to copy, do you tell it how many bytes to copy, or will it just copy the whole buffer?
That's a good question. So if you're okay with moving the thing, can you tell it how many bytes you care to copy? I don't think that's in the API. It's a good point. That would work if you had some like internal fragmentation going on. So maybe we should talk to Jason about this. It's a very good point. All right, so sort of David took my thunder with the very nice benchmark here. I'm going to only show you one benchmark. But this one benchmark, although synthetic, is very illustrative because pushback actually goes through the whole, it's all about resizing, growing the string, reallocating, the strategy of growth. So essentially, it's a walk through all of the essential string manipulation routines as related to buffer manipulation. So we have an exponential scale here. So I want to build, for example, at this size, I want to build a string of up to 64 characters by repeated calls to pushback. So I call 64 times pushback, right? Here I want to build like 64 kilobytes buffer by calling pushback, 64,536 times like an idiot. And again, this is not, it's a synthetic. Nobody would want to do this, right? And this is std string. And I should add std string in this test is also using gmalloc. So it's benefiting out of all the gmalloc advantages that are inherent to gmalloc. So what you see above 100% is pure gain by the strategies chosen by FB string. And we're looking, it's pretty obvious, like at small sizes here, we have a huge gain because there's no allocation at all, right? Up to, 16, 23, somewhere here, right? And then the relative gains are going to decrease, but interesting, they're going to plateau at a very significant 1.5 times faster, which is sustainable for long strings. So this is a very nice summary for the performance of the allocation strategies that FB string uses. So we learned in the process a lot of things. So FB string has all this all of this layout manipulation and stuff. I said it's doable. I didn't say it's easy. Last bug we found was this week. I'm not kidding. So we found last bug. No, it's not a lot. No, the latest. The latest found was this week. We found probably half a dozen bugs that were extremely insidious. And some had to do with assumption that people made about strings. Like, for example, some people assume the strings are always zero terminated, even though they didn't call sister, right? So they just think so. And it turns out that with GNU's implementation, it does so. It eagerly writes the zero terminator at all times. We thought, we're smart. We're going to write it lazily. Not going to work. So, we said, let's do when in Rome, right? Because we build our own GNU implementation library, so we said we're going to conform. So there's some assumptions and some bugs, but all in all, we've learned a very humbling lesson that untyped code is very difficult to write. It's 563 lines of code written with blood and tears, okay? And that many people have contributed to and improved. And it's a very humbling experience to see how much a type system can help. All right, let's move on and talk about, a less blood and tears kind of experience. Let's talk about a topic that is dear to my heart, parallelism. And I'm going to talk about the forgotten one. People have forgotten that you have layout control in C++. People tend to have forgotten we have parallelism in our CPU. There's been all this talk about data centers. This wonderful photo is our data center in Forest City, North Carolina. And inside that center we have the nice blue LEDs, and lots of them. And inside each of these nice bodies we have motherboards. By the way, just as a detail, the male model here, he's not a model, he's Amir. He's our hardware development manager. The muscle guy, and everything looking good. Yeah, that's Amir. He managed all this freedom servers thing. All right. So on the motherboards we have CPUs, and in CPUs we have, this is one core. So let me clarify. One core. That's why it's forgotten, because nobody looks inside anymore. Inside each core, we have 3 ALUs. And this is actually the old Nehalem core. The Sandy Bridge one has double as many. Is that correct, Jason? All right, so the Sandy Bridge core, I've been chatting yesterday with Jordan. So essentially, it has even more cores, so it depends on the CPU. And the question is, how do you use this? So let me clarify this. So you have the instruction stream and everything coming, and inside one core, you can do several arithmetic operations literally simultaneously within the same thread. Is this clear? Okay, don't forget this anymore, okay? We gotta use them, because otherwise this silicon is going to stay dark, and there's nothing we can do at a higher level to light it up. There's nothing we can do, Max. You can do hyper-threading, right? Hyper-threading, you need 2 threads to have hyper-threading. I'm talking about 1 thread. All right, I destroyed this guy. Perfect. All right. It would have sucked if I was like, all of this excited and everything. Oh my God, I didn't think of that. All right. So we have 3 ALUs or more. All modern CPUs have several ALUs that are ready for you to use, except often we don't. So the question is, how do we use them? And actually, inside that CPU, in conjunction with the compiler, there's a lot of stuff at work to expose and exploit this parallelism that allows us to use the ALUs. So there's pipelining, there's superscalar execution, there's triple O execution, there's register and renaming, there's speculative execution, there's branch prediction, there's a lot of stuff here, right? All of this is concerted and determined to find ways to parallelize serial code. What is does anyone know how effective these things are? Give me a fact, like twice as fast? Twice. Who gives more? 3, David. Who gives more? I should have that Texan accent here going, with the yeah. 5.
Wait, if it's just 3.
No additional question allowed. So you got to say a number. 100. Yes.
It depends entirely on the code optimization. Instruction ordering makes a huge difference on your ability to exercise those.
Instruction ordering makes a huge difference. And the point here is, automatically, on average, over multiple benchmarks, the number is 4.2x. 4 times as fast, which is, not too shoddy. I mean, you wouldn't want your program to run 4 times as slow, right? So, it does a pretty good job, but there are some algorithms that actually have so bad data dependency that you can't expose and find that nice instruction level parallelism. The key here is you want to have fewer data dependencies. You want your compute data in a way that's as little dependent as the previous line of code, if you wish, or the previous iteration in a loop, right? So as I said, this is almost always automatic, but there are important cases in which it fails. Is it important? Well, as I said, essentially if you took a thermal imaging of this thing and we don't use those ALUs, it would be the moral equivalent of sort of making this into a sort of a Swiss cheese kind of thing. You don't want Swiss cheese in a data center. It's going to rain inside and stuff, right? Or you don't want to take, this corner here, this portion here, you're going to open a Starbucks there because you're not using that stuff, right? No, you want Starbucks to open here, so people have a place to go just after work. Canned laughter, thank you. All right. So how do we minimize data dependencies? And I'm going to use an example. So take it as an example because it's not always essential to everybody, but it happens to be essential to us at Facebook because, again, we have a lot of numbers stored as strings. Let's convert a string to a number. String to integer. A to I. The absolute classic interview question. Hands up if this is familiar to you. All right. So, this is the core. We initialize the result with 0, and we say, well, every pass through the loop, we check that the digit is correct. I want to be between 0 and 9, right? And then I say, well, the result is result times 10 plus the last digit, right? And then, again and again and again. The problem here is each iteration in the loop depends in a very complicated pattern, like we have a multiplication, addition, and subtraction on the previous iteration, right? Well, how can we fix this? Ideas? All right, well, yes.
Exactly, okay. Expand the loop.
Expand the loop. Do unrolling.
I forgot. Yeah.
You're way ahead of me. Give me just a few minutes, okay? I'm gonna get to unrolling. Before that, let me actually write in math, in algebra, let me write down what we're doing here. We're writing down this number equals 0 times 10, because we start with 0, remember, assigned result 0. We start with 0 times 10 plus 5, everything times 10 plus 2, everything times 10 plus 3, and I don't have any more voice to sort of emphasize the amount of everything here. Everybody, that guy, okay. So essentially, this is ugly. And always ugly, not always, often ugly is a sign that we can do something better. Something is cheesy, amiss here. Something is not okay if it's ugly. Ugly code means bad algorithm, right? Ugly. Why is it ugly? Too many parentheses. Well, let's, at least programmers, let's not take this too literally. But essentially, parentheses in this context illustrate the fact that we want computations in a specific order. We want computations done, I want this first, and then I want that, and then I want that. Right? Parentheses are unnatural. They're forced. They must disappear from the face of the earth. In this case, again, I'm referring to math parentheses. So they force order. Well, let's just to throw an idea on the table. We could try some sort of divide and conquer kind of thing in which, well, this string has two substrings, this one and this one. And therefore, you could write this number as 523 times 1,000 plus, so as long as you compute these in separation, a simple operation is going to bring them together into the final result. Interesting, but not there yet. This is there. I mean, look how beautiful it is. I could actually align the thing. Look at, this is now, it's like one of those poetries in which there's an acronym here. There's a, what's the name? Acrostiche, right. So, we have the nice number here and there, the same thing, except there's multiplication by distinct powers of 10. Thank you for the photos. Look at that. Like, oh, okay, let me take a photo of that. It's beautiful. They didn't take a photo of the parentheses, So, now, there's no parentheses here. And that tells so much more. That tells so much more than one might think. What it says is you can do the multiplications in any order, and you can do the additions in the same order. Any order, sorry. You can do the additions in any order. There's no parentheses. Do you know why multiple additions don't need parentheses in algebra? Because addition has a property called associativity. Addition is associative. And this is something so awesome. I can't stand myself not telling you right now. Associative means parallel. Non-associative means data dependency means serial. All right? Gotta feel like on your spine a little flushy right now. Oh my God. Yeah. Oh man. All right. Let me rewrite the routine in that spirit with this new algorithm. Well, I'll tell you one thing. I'm very good at writing powers of 10. You see that big guy there? 1 followed by many zeros? That's the highest power of 10 that could be represented as 64-bit. And then we have the same guy, -1, 0, and we just back the zeros until we get to 1. So I have a big table with powers of 10. Why do I want the table? I don't want to compute powers of 10. I'm good at pasting them, right? All right, and the core of the loop here is, so we do the check, and we say result plus equals pow, the table at position I, and then we increment the position, so we get to the next smaller power of 10 times the digit. Where's all that parallel, or is that waxing poetic about, associative means that, this and that, and all that good stuff? Where is it? I didn't write anything parallel. I didn't write threads. I didn't write coroutines. I didn't write fork. I didn't do anything parallel. I didn't even care about anything. It's still dependent because there's plus equal here. Result depends on the previous thing. Except, at this point, the dependency pattern is very simple for GCC to unravel. And GCC is going to be smart enough to figure it out. This is the core of the loop, right? And look at this. It does more work than before because we're taking care of also incrementing this extra counter, and we have a table. So there's no actors in the play. So technically we do more work than before. And the question is this all worth it? Are we going to gain like 10, 15, 20%? So I told you I had a slide with it, coming with nice shiny colors. This is the point where, the spine and all that, chill on the spine, all that stuff, associative is parallelizable, right? It's all in the fundamental algebraic properties of operations, of algorithms, that allow us to do a very practical thing, such as parallelizing things, right? It's not some wacky, intuition or whatnot. It is a very fundamental property. And look at this. Just out of pure malice, I included boost lexical cast. If you want your code to be 12 times slower than A2UL, you're going to use string streams and stuff. Right? 12 times slower. All right? 12 times, 12x. I mean, that kind of number, you got to work really hard to get such a pessimization, right? It's not Boost's fault or lexical. It's the fact that they use a string stream, which is probably the worst abstraction ever. All right, so we have A2UL at 100% relative. We have Boost lexical cast. I'm going to talk about it anymore. And all of a sudden, we have an almost 2x improvement by doing nothing specifically parallel, just rearranging the algorithm. So if your program has 10% performance by, 10% of its time is taken by conversions, you're going to see a measurable increase, 5%. Let's make it faster. Your turn. I made it faster. Yes.
Enrolling to word size operations instead of byte operations.
Oh, sorry. He has the mic.
Can you use SIMD instructions?
Can you use SIMD instructions? You know what? Quite literally, we have top men on that. Because Eitan Frachtenberg, we were just chatting the other day, and he said, actually we could use SIMD with that, and there's a possibility that we can actually encode that loop in SIMD. Yes.
I'm sorry, I thought you were pointing at me. The loop unrolling to word size operations instead of byte operations for the subtractions.
Come again?
Unrolling to a word size and word size alignment on the byte operations. You can do, if everything is in range of the characters of 9, you can do subtraction in a single step on a word size int instead of byte by byte.
Right, so the point is, why don't you handle one word at a time? There are multiple issues with this. So first is there's alignment. And essentially spending time on figuring out where the alignment comes and everything is about as complicated as actually doing the whole damn thing, because the maximum iterations in this loop is going to be 20. It's not going to be 2,000 or 20,000 or 20 million. So it's not worth spending time on figuring where to start the loop. It's better to just start and go about it. Just give me a sec. And actually I tested, and Intel is pretty good at doing misaligned unaligned operations. But if you don't align, it's going to be like, 50% slower and stuff like that. So they got a lot better than, old days, but, it's still costly. Yes, Ben? Can you replace I with pointer arithmetic? Yes, but it's going to be slower. Why is it going to be slower? Someone else but Ben? Because at that point it starts messing up with GCC's alias detection mechanism. This, GCC knows we have one array and we have one index in the array throughout the loop. The array is static, const, whatever, it's never going to change. So it knows what it is. With pointer arithmetic, it all becomes, oh, this is a pointer, I know what the hell is going to happen here. So it actually generates slower code. Yes, make faster. Make faster. Yes. Thank you.
You can unroll the loop.
Unroll the loop.
Since it's only 20, so you can just put them in line, and then the compiler can make it much better.
You're ahead of me by a few slides, just like, all right. So loop unroll is going to happen, people. Stay calm in your seats, okay? It's going to happen. But let's make it faster another way first. Well, let's look at this test here and force, blah, 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 blah. 2 tests per iteration. Well, explicitated, we have if this, it's going to throw some error. It's not a correct string. It doesn't look like an integer, right? How do we replace these 2 comparisons with 1? This is what we'd like, minimize operations. So, this is supposed to be good. Yes? Unsigned. You're ahead of me, as usual. I'm getting old here. All right, so first idea I had was let's make it bitwise OR. So instead of logical OR, which says test this first, and then if this fails, test this second, serial, parentheses, right? Let's use bitwise OR. Don't get confused. The parentheses here are not for sequence, they're for grouping. So we have test this, make this test, and this test simultaneously, and then OR them. These two operations can be done actually literally in parallel. What's the speed gain? 5%. I'll tell you exactly. I'll tell you with any number of decimals, it's 0%. You know why? Because GNU does this. GNU takes this and generates the same assembler as for this. It's clever enough to have done that optimization for us already. All right, so don't, never underestimate the power of a compiler writer. Right? They can do magic. Of course, they can do this only because they figured there's no dependency between these two branches. Otherwise, it would have been bad, right? All right, so forget that. Let's use this digit. A table, tables are good, no computer breaks, so replace computation with tables. You know what? GNU generates the same code for this too. Right? I'm not kidding, it's the same code, 0% increase. All right, so let's do what Tom said we're gonna use. Let's use unsigned arithmetic. Unsigned arithmetic has an interesting property, which is called injectivity, which means if you add or subtract a number from another, the values are never going to, essentially there's no loss of information. You go around, there's never going to be a mapping. If you add the same number again, you're going to get the first number. There's no loss of information. It's conservative in physics. All right, this is very interesting. So let's cast to unsigned this character, subtract 0, and then compare against 10. Because we know that whatever was greater than digit 9 is going to become it's going to be a big number. And whatever is smaller than digit 0 is going to also become a big number. Unsigned is injective. It's never going to project two distinct values into the same value. It's what's called an injective function. Unsigned arithmetic is never going to put a wrong number into the range here. It's only going to take the wrong numbers, small numbers, big numbers, big numbers. That's it. It's modular arithmetic, right? Awesome. We replace this with one test. Two tests, one test. And actually, this is all smoke and mirrors because this is no operation. And let me clarify this. This minus here is the same assembler operation for signed or unsigned integers. Did you know? It's the same, sub. There's no sub u and sub s, right? It's the same operation. And it has that special meaning because of complement of 2. Awesome. Is it going to help? If I were an attendee, I would say it's going to help because look at this effect here. Did you see the flash? So this guy put a flash there, so he didn't put on the other two. All right. So the essential tidbit of information here is that we're talking about some arithmetic property that we translate into a beneficial algorithmic property. Modular subtraction has a property that allows us to use one test instead of two, and also addition has this wonderful property of associativity that allows us to do more of them in parallel in any order. This is key, not the numbers, although I'm quite proud of the numbers too. So A2UL, 100%. ILP, one test, we gain significantly more. We're beyond the 2.2x barrier. You know what? We've done it, so let's do it again. Let's make it faster, all right? All right, this time, let's actually think outside the loop. And right now, my thunder has already been stolen because it was like, unroll, 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 unroll. All right, unroll. So without the thundering voice and whatnot, so we're going to unroll now. All right, unroll. You want to unroll? I give you unroll. And I highlighted just one of the unrolls. So I did a four-way unrolling. four-way. Four ways unrolling means any cost that's to associate with an individual iteration is going to be slashed by 4, right? And, you know, I mean, here's the thing. This code is pasted, right? So I'm 43, okay? And I'm sort of past the range, past the age at which I would have done this with a template. And I'm before the age I would have done this with a macro. So I'm in this age where, you know, pasting this 4 times is okay with me. All right? It's all an age thing. You could try it with a template if you're young and, you know, and restless. So this is okay. 4-way unrolling we can handle with the editor. And what we do here at the bottom of the 4-way unrolling, we add all the 4 individual values, out of order, all that good stuff, right? And we increment the counters by 4, and we have some sequence at the end of the code to take care of the stragglers. No problem. Is this going to be faster? All right, okay, look at the effect. You see the flames? All right, it is faster. So we have baseline, we have 1.9228, 2.53. More than 2.5 times faster on an algorithm that nobody improved for 50 years. So this is with everything rolled in. So it includes the ILP, includes the fastest, and includes the unrolling. Yes?
So I have 2 questions. Did you check the bounds in the version with this speed up?
Question 1. Did you check the bounds in the version for this speed up? Because in the previous slide you were not checking the bounds, so that could be an issue. And while you're thinking about that, second question is, what? No.
That's inside the loop. So, yeah, I'm just, you know, it would be difficult to have the whole code. So the question is, did you check the bounds? The answer is yes, I did check the bounds.
Okay. The other question is, you know, GCC should have done this unrolling for you. So you kind of have to wonder what it is that you did that made GCC unhappy. And I wonder if the enforce macro might have something to do with it. So rather than have do the test, then if, then throw, you could count the number of errors that you had. And at the end, if you have non-zero errors, then throw. Because it's almost sure that the throw would make GCC go like, oh my God, I'm not going to enroll this loop automatically because there's some stake that can be asserted.
Right. All right, so to answer this, the first question, yes, we have all the bounds checked to the best of my knowledge. And actually, overflow is checked in an absolutely beautiful way, which I'm going to defer for a bit later. It's not going to be in this talk. Overflow, like if you have a very long string of digits, like 30 digits, you know, it's always going to overflow. So the overflow checking is wonderful because you actually look at the number of digits, and if it's smaller, you're okay. If it's greater, you're bad. If it's exactly that, you do a string compare against the largest representable integer, and I'm going to leave it at that because it's it's a beautiful thing. You'll have the occasion to see it. To answer the second question, what did you do to angry GCC, right? So after I angered GCC, there's some more point that you made.
Well, GCC does enrolling. So the enrolling, in theory, should have done nothing. So there is something in your code that makes GCC's enrolling not work.
Oh, and this is all this enforce. Yeah. All right. So the enforce is a sort of a small representation for sort of if this is not true, then throw, right? That was the expansion of it. And you know what? I'll tell you a secret. I am not above using GoTo. I am not above using GoTo. All right? And I go to, GoTo users anonymous meetings. I've seen a few of you there, so I'm trying, but I'm not above using GoTo. And let me tell you this, the actual code that you're going to be actually have an opportunity to see in its fullest actually has if D1 greater than 2, greater or equal to 10, go to somewhere here. And why here, not up? Because there's a maxim in, all compiler writers, there's a maxim, they say, go to forward is unlikely to be taken, go to backwards is likely to be taken. Everybody optimizes code like that. So if you want to go to that's unlikely, you want to go to forward in your code because you know that everybody is going to assume it's not going to be taken. And if you want to make a go to that's likely, you go back. Why? Because going back is very natural in loops. there's a lot of loops that just go to back, right? So everybody in the compiler optimization world is going to say, oh, this is a go-to going forward, then I'm going to assume it's not going to be taken. And that's what the CPU does too. It just assumes it's unlikely. All right, so there's some go-tos in here, honest. And there's a go-to and there's a throw here. And last but not least, you also made the point that, well, what if we sort of collect errors and do this and do that? Actually, I tried that, and it actually generates slower code. So, it's just an empirical fact that this is the fastest I could get without doing any sort of compiler-specific or process-specific optimizations. Yes, there's? Yes.
Why did you enroll 4 times?
Why did you enroll 4 times? It fits a slide. Thank you. You took that for me. Essentially, essentially 4 is about the smallest number. If you slash the looping specific cost by 4, it becomes negligible. And then you can take the risk of unrolling 8 times, 8 ways, right? Or 5 ways or whatnot, something odd. But you can unroll like many times, and then the code becomes big, and it can spill. So you have other risks. So 4 is about a good number for many unrollings. So this is a sort of a ballpark kind of scenario. Yes?
I'm basically repeating the question that gentleman asked. I can't see a bound check for I. There is a bound check for each digit to be between 0 and 9, but I is not checked at all. And what happens if the length is not divisible by 4?
What if so essentially, this is sort of the gist of it. But there's an adjustment at the beginning of the loop that takes care of it, and there's an adjustment at the end of the loop that takes care of it. So essentially, there's a longer story. What if you have a number that has 30 zeros and then some non-zeros? So the number has many digits, but many of them are zeros. So essentially what I do is I discount the zeros in the beginning, and then I operate on the rest, and the rest are guaranteed to not overflow the array. So there's a lot of details that go into this. So I try to focus on the essentials, while, please give me some credit that I took care of making this code correct. Yes?
You can collect all the enforcers together, turn them all into a single OR set with a single branch. This would also improve your iCache locality.
You can collect all the enforcers, so this is part of your point, right? You can collect all of the tests together, and because you can do it in any order, any way. And actually, this is the best. I try that. This is the best, because it's not only one test. You're going to have to OR everything, and everything. So you still have to do everything, right? If you collect them together and put them here, it's worse because actually the way these interleave is going to be suboptimal. Because actually there's three LUs, there's not 3,000. So, this test here is actually good to be inserted in there because it's an unlikely to be taken loop that's going to be fastest taken care of right here. So, but nevertheless, I think it's a reasonable thing to try. I tried, it didn't work. All right, so I have actually one more interesting thing. All right, speed up the flames. So, learn math. So, we've been doing all of this low-level optimization, all this stuff, but underneath it all, this is an injection, and this is a modulo operation, right? And this is associative. And you know what? I mean, at the end of the day, you can have all these intuitions, each on its own, right? But the math is going to offer you a very concise, useful, and complete framework for developing such intuitions. And these intuitions work for, I want to minimize traffic between data centers. Big algorithms, sort of, large-scale algorithms and sort of interesting, large processing problems. But it also can help you with the smallest things, such as how do I replace 2 tests with 1 test. So I would recommend, if there's any sort of overarching theme here, you should be learning math. You should know your math very well and should understand the relationship between a very practical problem and a very theoretical property. All right, this is my Steve Jobs moment here. One more thing. All right, so, you know what? So we've been talking about this good stuff, and you know what? Let's open source all this stuff. And we've been working on this for a couple of months, and we're very happy to actually open source FB string this wonderful conversion routine that we talked about, and a few more things into Folly, Facebook's open source library. This is the Welsh spelling, right? Library. All right. So we have quite a few. We have Spencer's wonderful atomic map that he's going to talk right after this. We have parsing and formatting utilities such as the conversion routine that we talked about. We have a few multi-threading frameworks and libraries, because we do a lot of threading at Facebook. We have a few general utilities such as a JSON parser and formatter, and a lot more. And what's most important, there's a lot more to come. We're going to have a lot more coming ahead of us. This is a foot in the door to starting to open source and giving back to the community a lot of value that we have sort of pent up in our core libraries. So we essentially would be so happy to open up a lot of our libraries, and there's a lot that depend on the small core that we decided to start with Folly. So we have, this is my contribution. This is a shell script that actually shows you how many people contributed to this and how many lines. And let me show you real quick. So this is the run of the shell script. I'm not sure if you see, but at the top there's Jordan. Say hello, Jordan. This is Jordan. All right. So I'm not sure if you see the numbers, but Jordan has 8,350 lines, and I have 8,318 lines. And just below me, there's Tudor Bosman, who has 8,205 lines. And you know why I have more lines than Tudor? I wrote a lot of the documentation. This is the secret. This is my secret weapon here. And then we have Spencer, who is going to give a talk today later. And we have Adam Simpkins. Adam, say hello. Hey, Adam. Thank you. Let's give Adam a hand, too. He's awesome. All right, is Xin Liu here? All right, Xin Liu is missing the applause, and then we have a long tail. So, all right. So you know what? When I leave my arm down, Jordan, you're going to open source this thing. Huh? They did it? All right. So much about my authority here at Facebook. All right. So open source. All right. With this, I'm going to end here on a sort of, weak note because you just uploaded. So thank you very much, and feel free to grab me in the break for any other questions you might have. Thank you.